Hi everybody, this is Tyson Gray for my CHE 815 Advanced Chemical Thermodynamics literature review. I decided to look at a paper called Modeling of Solution Thermodynamics, a method for tuning the properties of blend polymeric membranes by Krishnasri Kurata and Shendu Day. Sorry for butchering those names. So for the background, the polymer blending is one of the best ways to get desired polymer properties. They're looking at polymer blends. Polymeric blends are found in automotive parts, electric appliances, biomedical applications, and membrane filtration. And blending can control material properties like porosity, permeability, electrical properties, and surface hydrophilicity. So to go over some of the main parts that they will have in their paper, just real quick, polymeric membrane system parts. Their major polymer is the main polymer component whose properties we wish to fine-tune by adjusting other parameters. Minor polymer is a secondary component chosen for its molecular weight or membrane-forming properties. In this paper, the solvent they use that you'll see on the phase charts is dimethylformamide, otherwise known as DMF. It's a pretty common solvent. And they also have what's called a non-solvent, which induces phase separation, which is one of the main points of this paper. And for that, they use distilled water. So the polymer blend systems that we're going to talk about in this paper is polyacrylonitrile, or PAN, and polyurethane, or PUR. The focus of this work was to model the complete phase diagram for certain polymer blend systems. The thermodynamics of polymer blend systems are established using Flory-Huggins theory extended to be able to have four components by a scientist named Tampa. And evolution of the phase diagram curves include binodal and spinodal curves as well as the plait point. The modeled curves are validated with experimental work available in literature and pore dimension analysis. Membrane characteristics can be predicted with the models established by this work. So put simply, we have a spinodal curve here, and we use these phase diagrams to predict the characteristics of membranes made by different polymer mixtures. The theory in this paper, we've seen most of it in class. There are some things that might be kind of new, and one of those is the principle of phase inversion phenomena. So phase inversion phenomena can be explained by a simple example of an oil and water mixture. If you have just a little bit of water, you have water droplets dispersed in oil. And if you keep adding water, eventually you'll have a phase change where you have oil droplets dispersed in water instead. Per the authors, the kinetic study of phase inversion phenomena requires the knowledge of a complete phase diagram to identify the phase inversion mechanism as spinodal demixing or nucleation and growth phenomena. This mechanism of phase inversion in turn explains the formation of asymmetric structure in the case of spinodal demixing and symmetric structure in case of nucleation and growth. The spinodal curve signifies the limit of stability and is important in many membrane-forming models. So on the right here, you can see we have a spinodal curve, and then below that we have a binodal curve. And these phase diagrams are important in helping us understand the system, and with the system properties we see, we can actually predict properties of the membranes that will be formed from these polymeric mixtures. So to put it a little more simply, the binodal curve represents the initiation of phase separation and is calculated by minimizing the free energy. The plait point is the point at which the binodal and spinodal curves meet. The exact location of the plait point signifies that the minimum point obtained by the calculation is the true minimum in the given range. The changes taking place during the phase inversion can be correlated with the corresponding change in free energy of the system. The Gibbs free energy of the system is calculated based on the Flory-Huggins theory for polymer solutions, but extended to ternary and quaternary components by Tompa. The ternary and quaternary interactions of the system are very small, so for simplicity, the authors ignored them and only focused on the binary interactions. And I've taken just kind of the path they followed equation-wise. They used the Flory-Huggins theory for change in Gibbs free energy. From that, if you put those Gibbs free energy changes in a matrix and take the determinant of a Hessian matrix in particular, you'll get that determinant, which will give you the equation for the spinodal curve. And then just as an example, for one particular change in Gibbs free energy point, that's right there. The binodal equation is actually found by calculating the locus of the line joining two minimum points on the free energy curve. So we did something similar like that in class. At the binodal curve, the two separating phases are in equilibrium with each other and follow the condition of chemical equilibrium as the change in potential energy. And then here's an example of how they would calculate that. So one of the things that they're looking for in this research paper, and one of the things they're making actually, is this ternary phase diagram. And we touched on this briefly at just the last class we had. But on one axis you have the solvent, on one axis you have the polymer, and then on one axis you'll have the non-solvent, which induces that phase change. And that would be distilled water in this. So there's three main phases, or three main regions in this phase diagram. The first one, there's this homogeneous single phase. Over on this side of the curve, we have a two-phase region, and this is only a spinodal curve, but if we were to overlay the binodal curve, it would come down kind of like this, and in between the two curves would be a metastable region. So their results from the experiments actually came out pretty good. Here we have just kind of the graphing of the different polymeric blends. And then below we've got the four binodal curves of the different polymeric blends. So they didn't include the pure PUR, the pure polyacrylonitrile. You can kind of see that the cloud points, so these were actually experimentally derived and measured, matched the curves for the most part fairly well. Here in this curve, maybe not so much, but the rest of them lined up pretty well with the binodal curve, which is what you would expect if you have a good model. And on the right here, you can see that they took pictures with a scanning electron microscope and found that as you make your blends, you do seem to open up more pockets, which is what they were expecting too. So here you have pure PUR, here you have pure polyacrylonitrile, but in between you have membranes with different sizes of pockets. Another thing the authors looked at was how the effects of the molecular weight of the second polymer affected the binodal curves. And as you can see on this chart on the left, as molecular weight or mass increases, you can see that the binodal curve gets drawn closer to the solvent axis. And then on the second chart here, you see the variation of the binodal curve as you change the binary interaction parameter. And it's interesting to see how the spacings of your binary or your binodal curves will change when you change that interaction parameter. And lastly, they found some of the characteristics of the membranes as far as permeability and mean flow pore diameter goes. And as you can see, as they had more evenly distributed mixture, their permeability went up, which is in line with what we saw in those pictures of greater pocket sizes and more of them. And then the mean flow pore diameter also increased. So, in summary, the phase diagrams correlated well with known and experimental values, either from literature or from their measurements. These models were successful in predicting polymer mix characteristics, which is good. And then, just kind of as my feedback or whatever, I felt that the paper could have been a little bit more concise. They did kind of define their scope 3 different times, and it was a little bit different each time in the paper. And then some of the grammar was a little bit hard to understand. I had to read it again. But I'm sure that with my papers and even being an English speaker, that would be a challenge for me. So overall, I thought it was a pretty good paper, and they had some interesting results. Thank you.